In finding the complex root using exponential form, power of power rule is still used, making the procedure shorter. Welcome to Mathematics of Engineering. With z as r times e raised to I theta as the exponential form, the complex root makes the nth root of z as the nth root of the expression r times e raised to I theta. Place the radicals in rational exponents. The equation becomes z raised to 1 upon n as equal to r times e raised to I theta raised to 1 all over n. Distribute the exponent to get the nth root of z as r raised to 1 over n times e raised to I theta raised to 1 over n, where the latter exponents can be simplified through power of power rule, which states e raised to m raised to n as e raised to m by n. By following the rule, the nth root of z then becomes r raised to 1 over n times e raised to I theta all over n. Let's check the procedure in determining the fourth roots of z, which is 16 cosine of 120 plus I sine of 120 degrees. R is seen as 16 and theta is 120 degrees. Because exponential form uses radians, convert 120 into radians by multiplying pi over 180 degrees, giving 2 pi over 3. Place these parameters in the standard form to get the fourth root of z as the fourth root of 16 times e raised to y times 2 pi all over 3. Then multiply 1/4 or divide the exponent by 4. R is the fourth root of 16, which is 2. To take the four roots, recall that each of the roots is a revolution apart. That is 360 degrees or 2 pi. So for the first root, z1 is 2 times e raised to I times 2 pi over 3 multiplied by a quarter. This is simplified as 2 pi over 12, which can then be reduced to 2 times e raised to I times pi over 6. The second root is the same expression where theta is then added by 2 pi. Convert 2 pi into a fraction to add theta easily. 2 pi is 6 pi over 3, which is added to 2 pi over 3, giving 8 pi all over 3. This is multiplied by 1/4 to get 2 times e raised to y times theta, which is now 8 pi over 12. Taking a reduced theta, the final second root of z is 2 times e raised to y times 2/3 of pi. The third root of the complex number is taken by adding 2 revolutions to the vector. That is like adding 4 pi to the original equation. Make the equivalent fraction of 4 pi as 12 pi over 3. So added to theta of 2 pi over 3 makes 14/3 of pi. Multiply the root, which is 1/4, to have z3 as 2e raised to y times 14 pi over 12, which can be reduced to 2e raised to y times 7 pi over 6. The fourth root then considers 3 revolutions added to the vector's angle, that is 6 pi or 2 pi over 3. Convert 6 pi into an equivalent fraction, which is 18 pi over 3. Thus, z4 is then 2e raised to y times 2 pi over 3 plus 18 pi over 3, where theta is multiplied by 1/4. This then is simplified as 2e raised to y times 20 pi over 3 times a quarter. making z4 as 2e raised to y times 20 pi over 12. Theta is then reduced to have the final fourth root as 2e raised to y times 5/3 of pi. Another example is to find the fifth roots of z, which is 243 cosine of 4/5 of pi plus I sine of 4 pi over 5. The modulus is 243, and theta is 4/5 of pi. Using the standard exponential format, we take the fifth roots of z as the fifth root of 243 times e raised to theta of 4/5 pi multiplied by the root, which is 1/5. Simplify r as the fifth root of 243, which is 3. Again, each of the roots is one revolution apart, so start with the original vector. Taking the first root as 3e raised to y times 4/5 of pi, multiplied by the root of 1/5, this results to 3e raised to y multiplied by 4 pi over 25. The second root is then a revolution or 2 pi more, where 2 pi is then equivalent to 10 pi over 5. Add the original theta of 4/5 pi and get 14 pi over 5. Now simplify the exponent and have the second root as 3e raised to y times 14 pi over 25. The succeeding roots are computed similarly. The third root has 2 revolutions or 4 pi added. 4 pi is equivalent to 20 pi over 5. So add theta and get 3e raised to y times 24 pi over 5 multiplied by 1/5. Z3 is therefore taken as 3e raised to y times 24 pi over 25. The next root has 3 revolutions or 6 pi added. 3 revolutions is equivalent to 30 pi over 5. Add this to theta to have 34 pi over 5. Multiply the root of 1/5 to the exponent, which gives z4 as 3e raised to y times 34 pi over 25. The fifth root is solved by adding 4 revolutions, or 8 pi to theta. 8 pi is equivalent to 40 pi over 5. By adding theta, the argument is then 44 pi over 5. Multiply the root, which is 1/5, and get z5 as 3e raised to y times 44 pi over 25. Next is to find the roots of z cubed, which is I. In Cartesian form, the modulus and theta should still be computed. R is the root of the squares of a and b. A is the real number, which is in this case 0. B is the coefficient of the imaginary number, which is 1. R then solves the root of 0 squared plus 1 squared, which is equal to 1. When the vector is illustrated, it shows that it points upwards, which says theta as 90 degrees or pi over 2. Plug these parameters in the exponential form and get the cube root of z as the cube root of 1 times e raised to y times pi over 2 times the root, which is 1/3. Start with the first root with 1e raised to y times pi over 2 multiplied by 1/3. This is simplified as 1e raised to y times pi over 6. The second and third roots are revolutions apart from z1. z2 is then 1e raised to y times pi over 2 plus 2 pi multiplied by 1/3. 2 pi is equivalent to 4 pi over 2. Add this to theta and get 5 pi over 2. Simplify the exponent and get z2 as 1e raised to y times 5/6 of pi. The last root has 2 revolutions or 4 pi added. 4 pi is 8 pi over 2. Added to pi over 2 making Z3 as 1e raised to y times 9 pi over 2 multiplied by 1/3. Multiply the exponents and get 1e raised to y times 9 pi over 6, which is reduced to Z3, that is 1e raised to y times 3 pi over 2. Another example looks for the roots of z cubed, which is equal to -27. In Cartesian form, r is again solved as the root of -27 squared plus 0 squared, which is +27. Illustrate this to verify the argument. The vector points to the left, making the argument theta as 180 degrees or pi. Place these solved parameters in the exponential form and get the cube root of z as the cube root of 27 times e raised to y times pi multiplied by 1/3. The modulus is simplified as the cube root of 27, which is 3. Again, note that each root is 2 pi apart from the original vector. Z1 uses the original vector, and that makes 3e raised to y times 1/3 of pi. The second root is 3e times I raised to pi plus 2 pi upon 3, which makes 3e raised to y times 3 pi over 3. This is reduced to 3e raised to y times pi. The third root is 3e raised to y times the original argument of pi plus 2 revolutions or 4 pi. Then multiply the root, which is 1/3. Z3 is then 3e raised to I times 5 pi over 3.